Okay, hi everyone. Today we have actually two talks to look forward to. The first is by Louie. I guess you can explain to us how Louie is short. And this
Maybe over lunch.
Maybe over lunch. And second, we also have the pleasure of hosting Tim Roughgarden at the members' seminar. So to that, Tim will also be giving a public lecture on Wednesday. So, but now we will turn to Louie, who has done a lot of work on sparsification, CSPs, hypergraphs, codes,
and so on.
And today we'll hear about something else.
Yeah. All right, perfect. Yeah, so thank you for the introduction. And today I'll be talking to you about new parallel algorithms for finding matroid bases. And this is joint work with Sanjeev and Junkai, who are both from Penn. And so I know there might be some of you who don't know what matroids are. And so before I start, I just want to say at a very high level that matroids are kind of an elegant abstraction of many notions of independence that do arise in the study of combinatorial objects in theoretical computer science. And so for the first few slides, I'm really going to give you the formal definition of what a matroid is. And then I'm going to go through a couple examples to hopefully help you build intuition for the kinds of objects in matroids that we care about. And so to start, throughout this talk, I'll be denoting a matroid, M, by having a ground set E and a set of independent sets I. And so the ground set E contains n elements and is just an arbitrary set. And the set of independent sets is just a set of subsets of E. And importantly for us, this set I satisfies many convenient structural properties. In particular, I satisfies what I call the hereditary property, which says that if you have some subset S of elements, and that set S is independent, right? That set S is in I, then it must in fact be downwards closed, right? That every subset S prime contained in S is also independent. And a matroid also satisfies this thing called the exchange property, which says that if you have two sets S and T that are both independent, but that S is bigger than T, and in fact, there must be some element that you can take from S and give to T such that T retains its independence, right? That T union E is independent. And at first glance, it might not seem obvious why these are the definitions and notions of independence that we do care about. But it turns out that there's many examples of matroids that arise in theoretical computer science. In particular, one of the most canonical examples of a matroid is what's called the graphic matroid. Here, you're given a graph G with vertices V and edges E. You can define a matroid over the set of edges in this graph. In particular, for some subset S of the edges, we can say that S is independent if and only if S contains no cycles. And I won't prove to you that this is a matroid, but indeed, if you define the independent sets exactly in this manner, it will in fact yield a matroid. And this is called the graphic matroid. Another canonical example, another motivating example for the study of matroids is what's called the set of linear matroids. So here you're given a set of vectors. Your ground set E is just a set of vectors V1 through Vn. And now we say that a subset S of these vectors is independent if and only if the corresponding set of vectors is linearly independent. And so in fact, this will be a very useful example to keep in mind throughout the talk when trying to gauge which properties of matroids hold true. There's also some simpler classes of matroids that we'll be using throughout this talk. The first of these is something called the uniform matroid. Here you're given a set, again, of n elements, and you're also given a budget parameter E. And now when you look at a set of elements, we say that such a set S is independent if and only if the size of S is less than or equal to B. And again, I won't prove to you that this is a matroid, but hopefully you can see, for instance, like the downwards closure is trivial. And now you can also generalize this notion of uniform matroids a little bit farther to something called a partition matroid. And so what you do here is that you take your set of elements E, and now you partition it up into a set of disjoint parts, P1 through Pk. And now each one of these parts is assigned its own budget. And so this really becomes, a disjoint union of uniform matroids on subsets of the elements. And so what that means is that a subset S is independent if and only if it doesn't exceed the budget in every single one of these individual parts. Right, that S intersect PI is less than or equal to BI. And so, okay, so far I've just given you a couple examples of what matroids look like, and we'll actually revisit these in just a couple minutes. But it turns out that one of the key features in the study of matroids is that there's objects within matroids called circuits and bases, which are actually very fundamental combinatorial objects in their own right. And so in particular, throughout this talk, I'll frequently be referring to circuits and bases. And so I will define them here, but then again, we'll revisit them with examples on the later slides. And so a circuit in a matroid M is given by a subset of elements, which is a minimal dependent set. And so what this means is that the set of elements C is dependent, but that if you remove any element from C, it becomes independent. So it's a minimal dependent set. Kind of on the opposite end of the spectrum, you have something called a basis. Again, a basis B is a subset of elements, which is now a maximal independent set, right? Which means that B on its own is independent, but if you take any other element and add it to B, it now becomes dependent. And now just for kind of sake of clarity in later arguments, I will also define the rank of a set. And so for a set S, we say that the rank of a set S is just the maximum size of an independent set that's contained in the set S. But anyways, with these notions established, let's revisit these examples that we just looked at on the previous slides and see what exactly circuits and bases correspond to. So again, in this graphic example, right, a basis will be any maximal set of edges that contains no cycles. And hopefully you can see for yourself that then a basis is exactly a spanning tree, or maybe more formally, a spanning forest of the graph G. A circuit is again a minimal dependent set. So this would be the smallest possible minimal set of edges which contains a cycle. So then kind of by definition, a minimal set is then necessarily just a single simple cycle on its own.
Can't it be like a union of cycles?
But then it won't be minimal, because if you delete some elements, there would still be a cycle left.
Oh, right.
So it has to be a minimal dependent set. But great point, yeah.
Yeah, okay, sorry.
Yeah. Again, in a linear matroid, you can also look at these analogous notions, right? So what is a basis in a linear matroid? Well, it's a maximal set of linearly independent vectors. Okay, well, that you just call a basis anyway, so it's very easy to understand. A circuit is maybe a little bit less well studied. And so a circuit is somehow any set of linearly dependent vectors, such that if you deleted any single one of them, it would become independent. And maybe a little bit less well studied, but still certainly well defined. Likewise, in the uniform matroid, a basis is just any set of B elements. A circuit would be any minimal set of elements which exceeds your budget B. And so then necessarily it would just be B plus one elements. And again, you can also extend this to partition matroids. So again, a basis would be any set which exactly meets the budget in each one of your pieces. And a circuit would mean that you exceed the budget by one in exactly one piece. So hopefully, okay, at least I've given you some intuition for what matroids look like. And so then I can really tell you what I'm going to talk about today, which is the task of finding a matroid basis. And hopefully from these previous slides, you can already see that this task of finding a matroid basis does generalize very many natural tasks in optimization. So for instance, in graphic matroids, finding a basis corresponds to finding spanning forests. And in these linear matroids, it corresponds to finding bases of these spaces. And I won't really get into these other applications, but it turns out that finding matroid bases is actually an important subroutine in many other combinatorial optimization algorithms. And I've put some pointers on the slides here in case you want to look them up after the talk. But they have applications to matroid intersection and optimization under matroid constraints. And now, one important caveat that I need to mention before we talk about algorithms for finding matroid bases is that it's actually very hard to represent matroids. In particular, once you fix the number of elements n in the ground set of the matroid, the number of possible matroids on n elements grows super exponentially, right? It grows as 2 to the 2 to the n. And so you cannot hope to describe these matroids in a succinct manner. And so in general, when we talk about algorithms for finding structures in matroids, including finding bases of matroids, we often rely on oracle access to the matroid. And so all this means is that throughout this talk, whenever I talk about access to the matroid, this is only provided through something called an independence oracle. So in particular, you get to specify some subset S of the elements. You get to send it over to the oracle, and the oracle will tell you whether or not that set S is independent. Right? It's just telling you whether or not S is in the set I. But already with this kind of access to the matroid, right? This kind of independence oracle access to the matroid, I claim that finding a matroid basis is actually very easy, the greedy algorithm. And in fact, this is a very good piece of intuition to have for matroids, right? There's somehow combinatorial structures where the greedy algorithm, and in general, variations of the greedy algorithm do very well. And so let me even present to you right now a very simple one-slide argument for how you can find a basis of a matroid just using an independence oracle. So what are we going to do? We're going to initialize a set B of elements, which is all the elements we've chosen so far to build our candidate basis. And so to start, this set B will just be the empty set. The set F will just be kind of the buffer of all the remaining elements that we have yet to look at. So again, initializing, we have B to be the empty set and F to be all of the elements in the matroid. And now this is all the algorithm is going to do. While F is not empty, take one element from F, right? Take the next element from the buffer and check whether you can add it to your candidate basis B. You're just going to query the independence oracle with B union E. And if this is independent, it's saying, okay, yeah, you can add this and still retain independence. And if so, great, let's add it to the set B. Otherwise, we're just going to throw that element away. And we're just going to repeat this, I guess there's n elements, so you repeat this n times, and it claims that at the end of this procedure, you do indeed return a basis of the matroid. And this is actually more or less definitional if you think about what a basis actually is. Right, so a basis is any maximal independent set, which means that any other element that you could add to the basis would cause dependence to arise. And now let's think about which elements did we not add to the set V. Well, it's exactly those which cause dependence when we tried to add them. Right, and so there you can see, okay, this isn't certainly like a very canonical and greedy algorithm, which does indeed give you a basis of a matroid. Today, however, we're not just going to be talking about any algorithms for finding matroid bases. Instead, we're going to be talking about parallel algorithms for finding matroid bases. And in particular, the question we're going to ask is how many adaptive rounds of queries are needed to find a basis of a matroid when each round can only make a polynomial number of queries in parallel. So a little bit more formally, the kinds of algorithms that we'll be studying in each round are allowed to make a polynomial number of queries to the independence oracle. And this is in the standard kind of adaptive model of complexity, where the queries in round I are only allowed to depend on answers to queries in rounds 1 through I minus 1. Right, so you're sending out like a batch of queries all at one time in round I. And the goal is to try to find a basis of the matroid in the smallest possible number of rounds. And so if we just think back to this greedy algorithm that we saw on the previous slide, the greedy algorithm is really making n adaptive rounds of queries. Right? And in this setting, we even have that each round is exactly one query. Right? And this is because the query in round I depends on whether or not you included element I minus 1 inside the candidate basis B. And so the key question that we'll be talking about today is whether we can find a basis with fewer rounds of adaptivity. And I do want to mention that this is really a question that was posed by Karp, Upfal, and Wigderson in a seminal work in 1985. And their exact wording of the question is, what is the round complexity of finding a matroid basis with independence queries? And it turns out that already in this work in 1985, they gave a very non-trivial algorithm for finding matroid bases. In particular, what they showed is that there's an order square root n round deterministic algorithm which finds a basis of an arbitrary matroid using only a polynomial number of independence queries per round. Right, so this is saying that somehow beyond this greedy algorithm, which takes n adaptive rounds of queries, there are lots of non-trivial optimizations that you can do when it comes to finding matroid bases. Fortunately, this algorithm is actually pretty easy to describe, and I think it's a great way to build intuition for which properties of matroids you can expect to hold true. And so I'll actually go through the description of this algorithm together. And so the actual workings of this algorithm is very similar to the greedy algorithm that we just saw. And so in particular, in order to find a basis of the matroid, you first initialize your candidate basis B to be the empty set. And you also initialize a set F of all the remaining elements that need to be processed. But the idea now is that instead of just trying to process one single element in each round, the goal is going to be to process square root n elements all together in each single round of queries. But in order to do this, we also have to be careful about what structures we maintain in the matroid during the execution of this algorithm. So the first, just as before, we're always going to maintain the invariant that B is an independent set, like that our candidate basis B is independent. And we're also going to ensure that rank of F union B equals rank of E. And the way to interpret this is just that once the algorithm has terminated and F is the empty set, we want that rank of B equals rank of E. And this just means that the set B is indeed like a maximal independent set. It is the largest possible that you could hope for. Okay, so this is just a high level intuition for how the algorithm operates. But now let's actually take a look at how it goes down. So again, let's imagine that we have the n elements in the matroid, which I've just put up here as E1, E2, all the way up to En. And the goal, again, was to process square root n elements in each round of this procedure. So what do? We're just going to break this up into square root n groups of square root n elements. And so on the left, we have the first bucket. It has E1 all the way up to E square root n. And on the right, we have the last group of square root n, right? The square root nth bucket of square root n elements. And the actual queries that the algorithm does are very simple. All you're going to do is that within each group, you're going to query all prefixes of elements. So what does this look like? Let's zoom in on the first bucket for now. So let's look at those elements E1 through E square root n. And again, as I promised you, the queries are all prefixes. So what this means is that you query just E1, then you query E1, E2, then you query E1, E2, E3, all the way on until you query the entire bucket in the final query. Again, these are all done in parallel, so it's just one round of queries. And so let's think about what happens. Right? Let's imagine, case one, that when you query all square root n of these elements, the query is in fact independent. This is actually great news for us, right? It's almost saying that, look, we found a whole group of square root n independent elements. And so we're just going to take those elements and add them to our basis, right? You're just going to commit to keeping E1 through E square root n inside your basis B. The more subtle case is when this doesn't happen. All right, so imagine that the final query you made on all square root n elements was in fact dependent. What this means, though, is that somewhere along this chain of all your prefix queries, the queries went from independent to dependent. And so what I claim is that if you identify the first element EJ, such that the prefix query E1, E2, all the way up to EJ is dependent, then you can actually just delete that element EJ while preserving the existence of a basis. And so it might not be immediately clear why this is true. But one way to build intuition is to think about linear spaces. Right? Imagine that E1 through EJ are just vectors in some linear space. And that E1 through EJ minus 1 were linearly independent on their own. But that when you added the jth vector, E sub j, the collection became linearly dependent. The only way that this is possible is that EJ is in fact in the span of the first j minus 1 element. And so somehow it's not contributing, it's not like a fundamental direction in the linear space that you need to keep in order to compute a basis. So with this said, this is the entire outline of the algorithm. Right, what are we going to do? Within each group of square root n elements, we're going to query all prefixes. If some group finds square root n independent elements, we're going to commit to keeping those in the basis. Otherwise, every single group has found an element to delete. And so we're going to delete all of those square root n redundant elements. They're square root n groups. And the claim is that this then reduces basis finding on n elements to basis finding on n minus square root n elements. And so if you just look at the recursion, after only order square root n rounds of this recursive process, it will in fact give you a basis of the matroid and just order square root n rounds. Great. Any questions or?
So,
yeah,
I mean, you're trying to optimize the number of rounds and the number of operations within every round. Can you be?
So within each round, we're happy to just make any large polynomial, like a n to the c for any constant c. What we're really focusing on is the number of rounds.
Okay.
So here, within each round, you're making like order n queries, but we don't care so much about that. We're happy if it's even n to the 100. It's really just the number of rounds. So again, here at square root n, can you do better?
So the union of two independent sets is not necessarily independent.
Yeah, so the union of two independent sets is not necessarily an independent set.
So suppose you find root n independent elements in some round, and then you find a basis for the remaining n minus root n, then you can't just union them.
Great, great. So this is a great point. So he's saying, right, all I've said is that in round one, you find square root n independent elements. But in round two, how are you guaranteed that you can add the next, say, batch of square root n independent elements on top of those already existing square root n?
It's adaptive, no? You do with the prefix.
Yeah, you just do it. Exactly. So, yeah. So the answer is basically, you're going to include that first set of square root n inside all of your future queries, right? So you're basically committing to keeping those before you continue on. Perfect. Great. So then this kind of naturally motivates the following question of, can you actually do better than square root n rounds? And this was also a question that Karp, Upfal, and Wigderson looked at in their work. And they weren't able to completely close the gap. But what they showed is that any randomized basis finding algorithm that uses only a polynomial number of independence queries per round requires omega tilde n to the 1/3 rounds to find a basis. So there's like a pretty big polynomial lower bound. But importantly, it doesn't completely close the gap. And in fact, just as an aside, this lower bound is in fact quite rudimentary. And it only relies on partition matroids, those matroids that we saw on one of the example slides. And we'll even go through this example later on. But nevertheless, this leaves like a pretty big gap in our understanding of the parallel complexity of finding matroid bases, right? Does the complexity look more like square root n, or does it look more like n to the 1/3, right? It's bounded somewhere inside this gap. And so this is the question that we set out to study. And so what we showed is that, in fact, you can do better than this upper bound. Right, so what we showed is that there's a randomized basis finding algorithm, which uses only a polynomial number of these independence queries per round, but which can compute a basis of an arbitrary matroid in just basically n to the 3/7 many adaptive rounds of computation. For those of you who aren't good with fractions, 3/7 is like 0.429. And the reason this is a nice theorem is, one, because it shows that the square root n round algorithm, which feels like a very natural, greedy algorithm for finding a matrix, maybe not exactly greedy, but some kind of variation of a greedy algorithm, is typically the kind of reasoning that works very well on matroids and gives optimal algorithms. But as we'll see, it turns out that for this problem of finding a matroid basis, there's actually much more intricate algorithms that you can use that actually outperform this square root n round algorithm. And again, as corollaries, because of all these applications of matroid basis finding, you can naturally plug this into these other algorithmic problems and get better complexities, for instance, like matroid intersections.
So do you think 1/3 is the
Yeah, so I guess I do think that n to the 1/3 is the right answer. I don't know if one way to think about it is that there's no nice numbers between 3/7 and 1/3. So, but I can give you more evidence for that later maybe. But yeah, and one other reason maybe to think that n to the 1/3 is the right answer is that for this class of partition matroids, which again is the set of matroids for which Karp, Upfal, and Wigderson showed their lower bound of n to the 1/3, using our algorithm for general matroids, but kind of specialized to the setting of partition matroids, actually shows that n to the 1/3 is basically optimal, right? That for any partition matroid and n elements, the best you can do for finding a basis is the best lower bound you could hope for is basically n to the 1/3, right? That this is essentially tight. So for any partition matroid, you can find a basis in just O tilde n to the 1/3 rounds of a polynomial number of independence queries.
It's not the same algorithm as the one you're going to show us.
So you'll see the high level structure is actually very similar. And this is a great point. So for the rest of the talk, I'm actually going to focus first on the setting of partition matroids. This is a really good way to build intuition for how these kinds of algorithms on matroids operate that we design. And then with the last bit of the talk, I'll actually show how you can specialize this to general matroids. It actually reuses a lot of the same definitions in machinery.
So the deterministic best bound is still root n?
Yeah, that's a great point. So the best deterministic bound is still square root n. And it's a great point. So like in this theorem, when I say this is actually a deterministic algorithm for partition matroids,
Okay.
but the way we achieve the derandomization is just by taking a union bound over, there's only an exponential number of possible partition matroids. For general matroids, there's a super exponential number of matroids. And so you actually can't just do like probability amplification and then take like a non-uniform query set. So de-randomizing these algorithms in general matroids is actually a very difficult problem, even to do it non-uniformly. It's great. And so for the remainder of the talk, I'll actually first talk about this n to the 1/3 round upper and lower bounds for partition matroids. And then with the last bit of the talk, I'll actually specify these algorithms to arbitrary matroids. I won't actually give you the 3/7. I'll actually give you a 4/9 round algorithm. It's a little bit simpler to describe. Great. And so let's then start with tight bounds for partition matroids. And so again, Karp, Upfal, and Wigderson, they showed this lower bound of n to the 1/3 adaptive rounds for finding bases of partition matroids. And for those of you, I'll just refresh what partition matroids are. Again, you have your n elements, you partition them up into these k parts. These are disjoint parts P1 through Pk. And we say that a set is independent if and only if it doesn't exceed the budget in each one of these parts. And so in particular, a basis is a set which has exactly bi elements from each one of these parts.
Is it always true that a particular product of matroids is a matroid? It's like a particular product, right?
Sure. If you take like a disjoint union of matroids, that'll still be a matroid. Yeah.
And your algorithm doesn't know the partitions, right?
That's a great point. So when I describe the instance, the first thing I'll do is I'll randomize the elements. Exactly. So you could imagine if the algorithm did know which elements are in which parts, then it's basically trivial. So I'm going to assume that we're actually going to construct like a family of matroids, which are constructed by like randomly assigning the elements to different parts. Right. So our lower bound instance, we take our n elements and we then randomly partition them into n to the 1/3 many different parts. Right. So you have P1 through Pk, k equals n to the 1/3. Naturally, if there's n to the 1/3 parts, then the size of each part is n to the 2/3. And then the last thing that we do is we have to specify the budgets of these different parts. And so what I'll do is I'll say that the budget of the ith part is I times n to the 1/3. Right, so you basically have like a staircase of increasing budgets. Right, and the claim is that this instance, any algorithm which claims to find a basis of this instance of partition matroids requires n to the 1/3 many adaptive rounds of queries. And let's see why this is the case. Right, so in round one, let's take some query Q. Right, so it's some subset of the elements E. And you're checking, is this an independent set or not? And the first claim is that any query Q essentially corresponds taking a random sample of magnitude q many elements. Right, and this is just because we randomized the labels of the elements at the beginning by randomly partitioning them into their buckets. So any query, right, it doesn't know this randomized labeling scheme. And so no matter what you do, it's basically just a random sample of magnitude q many elements. And now the key point I claim is that whatever the answer is to this query q, it's almost completely governed by the size of q intersect p1. Or let's say it's almost completely governed by how many elements q has in the first part p1. And let's see why this is the case. Imagine that your query q is big. Right? Let's say that's of size at least 3/2 times n to the 2/3. Right? How many elements do you then expect to land in part p1? Right, well, there's n to the 1/3 many parts. And so a random sample of 3/2 times n to the 2/3 many elements, you'd expect basically 3/2 times n to the 1/3 many elements to land in part p1. And okay, you can do a Chernoff bound, but basically with very high probability, the size of q intersect p1 is bigger than n to the 1/3. And right, what's the budget of part p1? Well, it's also n to the 1/3, right? So with very high probability, you've exceeded the budget of part p1, and so the query will be dependent. But importantly, right, the query is dependent because of the dependence in part p1. And now let's look at the other case, right? Imagine that q is smaller than 3/2 times n to the 2/3. Okay, it could still be the case that a dependence arises in part p1 by the same logic as before. But importantly, what I claim is that q does not exceed the budgets of p2 through pk. Right? For the same reason as before, right? You expect only 3/2 times n to the 1/3 in each bucket, but those budgets are all at least 2 times n to the 1/3. Right? And so none of those other buckets will have their budget exceeded. And so the dependence depends only on what happens in q intersect. Is there a question or? You get it? Okay.
I'm good. Yeah, sir.
Perfect. And so again, the intuition is that this entire procedure should just tell you that even if you made a polynomial number many of queries q, basically all that you're learning in this first round of queries is information about p1. And you're learning very, very little about the later parts p2 through pk. And by the same logic, you just want to like iterate this argument and say that in the next round, you basically only learn p2, and in the round after that, you basically only learn p3 and so on. And because our original instance had, n to the 1/3 many different parts, well, this should tell you that, okay, maybe you should expect that the algorithm requires omega, n to the 1/3 many rounds to find a basis of this set of partition matrix.
So Louis, should I think of this as like, in the second round, you're maybe giving me for free all of P1, so now I'm
Exactly.
free to learn P2 and so on.
Exactly, yeah. So after round 1, I'll even give you the complete identity of P1, and then I'll task you with trying to learn, what is P2. Great. But there should be something a little bit unsatisfying about what I just told you.
So,
Yeah.
so are you going to talk about the algorithm again? Or can you repeat that? Like the intuition, how you
For the lower bound? Yeah.
no, like you said, like there's a matching upper bound, right? There's the same upper bound.
Yeah, so I'll get to that in a second.
Okay.
But there's something a little bit unsatisfying about this lower bound, right? Which is that, at least from the reasoning that I gave you so far, you should expect that you can actually get a better lower bound. Right? What if you look at the other instance, where now instead of n to the 1/3 many parts, you actually have square root n many parts, each of size square root n, and where the budget of the ith part is I, right? So it's the same staircase of increasing budgets, but now all of their sizes are bounded by square root n, and now you have square root n many of them. Right? If you could repeat the same logic about arguing that you only ever learn about P1 and then P2 and so on, it would give you a matching lower bound for this instance, or you get like a square root n round lower bound for this instance of matroid. Right, and that would be great because we already know the square root n round upper bound, and so it seemed that then you can like completely resolve the question. But it turns out that's actually not true. You can do much better than square root n rounds for learning this kind of partition matrix. And let me give you some intuition for this. And this will actually be very useful intuition when we actually go to the upper bound algorithm, which is why I'm going through this. Right, so suppose that an algorithm has learned the first I-1 parts of the partition matrix, and then the only parts pi through p square root n remain. And now again, let's consider a query Q such that in expectation, Q picks up I elements from each part. And so we've learned that first I-1 parts, only pi through p squared n remain. And so we're going to do a random sample of elements such that in expectation, you get I elements from each part. But now let's look at a question. How is the size of pj intersect q distributed? Right, so pj is just an arbitrary part. How big is pj intersect q? And so kind of by construction, right, in expectation, we wanted to get I elements from each part. So necessarily the mean is I, we expect I elements, but importantly, there's a standard deviation of square root I. And it turns out that this standard deviation will be the key to designing a better algorithm. And why? Because it means that with probability omega 1, you can have both that you exceed the budget in pi plus square root I, while that you don't meet the budget in p sub I. Right, so here you've sampled I plus square root I elements, so you exceed the budget in pi plus square root I, but here you've sampled less than I elements, so you haven't exceeded the budget. And so the same kind of lower bound argument that we looked at before, well, I'd want to say, okay, the query only depends on the answer to q intersect p sub I. But that's not true anymore, right? In fact, you can design queries where the response to the query depends uniquely on any one out of these objects, right? If you do enough samples, you can make it depend on all of these different parts.
So this is because in round one you had like 2 and 3, but now I have I versus I plus 1 or something. So when you do the Chernoff bound, there's this variance.
Exactly. Great. Right. So and I think why did the other example work? Right. It's because like the budgets were always increasing by multiples of n to the 1/3. And the sizes were n to the 2/3. So the square root is exactly n to the 1/3. So that's why you get the nice separation, right? And that's why n to the 1/3 is such an amazing lower bound, right? So it's really the trade-off between the standard deviation and the size of the pieces. And again, I won't go into the formal argument for this, but it turns out that you can actually go through in this example and learn the identities of parts pi, I plus 1, all the way up to I plus square root I in just one single round of a polynomial number of queries.
So could you explain this a little bit more? Like, yeah, I see that this argument holds, but because you want to learn like all of them, like in one round, it seems like you need to sample a lot of like to specify for each coordinate, like you have a sample like hitting the.
Exactly, right. So you really need to, exactly. You want to say that you uniquely hit each one of these parts in some sample. And so the way that you'll do this is you'll actually sample like I minus like square root log n times square root I. So like you want mean to be several standard deviations below, like square root log n standard deviations below. And then most of the time no one is hit. But when you have these rare outlier events, someone will be hit. So there is a way to formalize it just by.
Okay. I think
But anyways, I promised you an algorithm that works for all partition matroids, right? So how do we generalize this to all partition matroids? For this, I just need one warm-up claim, and I won't really go into too much detail on this, but I'll at least give you a picture to describe what exactly I mean. But so given a partition matroid P1 through Pk, I claim that you can recover the identity of some part in this partition matroid in just 2 rounds of queries. And so in particular, I have like a very specific algorithmic framework in mind. And so what I mean is that let's imagine that you have your partition matroid. So here it's very simple. There's 6 elements. Each part has 3 elements. The budgets are both 1. Very simple example. But I'm really referring to a specific process in mind, where what you do is that you sample a random permutation pi over all of the elements. And now you do all of your prefix queries on these elements. Right, so here, if pi of 1 was the first element, you would query just this element on its own. If pi of 2 is this other element in P2, then you also query that element, right? Pi of 1 and pi of 2. Maybe pi of 3 is this other element in P2. And again, you query pi of 1, pi of 2, and pi of 3. And so my point is that when you do this procedure, eventually you'll get to a point where you get your first dependent query. And I claim that it'll always be because you've exceeded the budget in exactly one of these parts, right? Here, for instance, you've only exceeded the budget in part P2. And so I won't exactly go into how you can do this, but it turns out there's a pretty cute algorithm which says that you can find exactly which elements caused the dependence. Right, so you can find which of those elements out of all three of these were the reason for the dependence, right? So here it's exactly those two elements in P2. And once you've done this, you can really learn the entire part. Right? Once you know those two elements, you can also learn the other elements in the part. And so it gives you a mechanism for learning the part which first caused the dependence in this random permutation. And so I won't really go into more detail than this, but hopefully we can at least black box this claim going forward.
Where did you need a random permutation for?
Yeah, so you don't actually need a random permutation. I only did this because we'll see in the next slide that we do need a random. That's a great point, though. This works even without a random permutation. Great. But so with this, let me actually give you the algorithm, right? It'll be like 2 lines of pseudocode, and that's the entire algorithm for finding an optimal algorithm on partition matrix. So what are we going to do? Here we use the random permutations. We're going to sample a polynomial number of random permutations. And then for each permutation pi, we're going to run this algorithm from the previous slide, right? So it'll find for each permutation pi, where was the first dependence that arose? And it's going to recover the part that contributed that dependence. And then you just take the union of all of these recovered parts. If you're in the round I of the algorithm, we'll call that S of I. And then you'll remove S of I. Right, and so all I claim is that when you run this algorithm, it will only ever run for n to the 1/3 many rounds. As in particular, if S1 through Sk are your recovered sets, I'm going to show you that k is just O tilde n to the 1/3. And so at this point, what does it tell you? Well, it tells you that you've basically learned the entire structure of the partition matroid and just n to the 1/3 many rounds. Right? It's in fact stronger than this basis finding question. You know exactly which elements are in which parts and which budgets they have in that part. Like you've completely learned the entire instance.
So you mean that by n power 1 over 3 rounds, Sk will be empty?
Yes, exactly. But so there's one challenge that arises here, right? So in this previous example that we looked at with square root n parts with the staircase of budgets, whenever we talked about, how do we make progress, we were always looking at, okay, which budgets have been recovered and so on. In general, the structure of partition matroids can be a little bit more intricate than that, right? You can imagine that when you recover a set Si, it's really, a union of individual parts. And so there's not a clear notion of what's the budget of a set of elements that contains multiple individual parts. And so one of the key challenges in this direction is to come up with an appropriate definition that's a robust notion of budget that we can use to measure progress. And so to do this, we introduce something called the circuit trigger parameter. And this is really one of the key definitions. And will also appear later when we talk about algorithms for general matrices, when we extend beyond partition matrices. And so again, for a set S of elements, the way we define the circuit trigger parameter, which I denote by alpha of S, is it's the smallest integer L, such that with probability 1/2 over a random sample of L many elements, your sample is dependent. Right? An equivalent way to view it is essentially as when you do this random permutation experiment, what's the median number of samples you have to look at before a dependence arises? Right? What's the first point at which this probability of becoming dependent exceeds 1/2? And so a little bit maybe more informally, right? If alpha of S is super small, right, it's telling you that pretty early on dependencies are arising when you do this random circuit experiment. So smaller alpha of S implies dependence occurs early. And maybe one way to think is that maybe the set S has lots of extra elements then that you can delete. Maybe that this is like a deletion round of the algorithm. If alpha is really large, right, it's telling you that S contains a large independent set, right? Because indeed, if you did a random sample of alpha of S minus 1 elements, that would in fact be independent with probability at least 1. And just to let it sink in a little bit more, sorry, this is say a uniform matroid, right? If S is just a uniform matroid with budget B, then you can ask, okay, when would the first dependence arise? Well, it would arise when you've sampled B plus 1 many elements, right? Kind of deterministically, it'll always happen after the B plus first sample. And so this is the key thing to keep in mind, right? The circuit trigger parameter, which is the median location of when dependencies arise. And so with this established, the key lemma to bound the number of iterations in our preceding algorithm is the following growth rate lemma. And so imagine that you've peeled off sets I and Si and Sj, and some rounds I less than j. The claim is that it satisfies this kind of messy looking recurrence. But let's simplify it. Let's imagine that Si and Sj are in fact the same size. And then magnitude Si is approximately equal to magnitude Sj. What is this telling you? It's telling you that alpha of Sj is at least alpha of Si plus square root alpha of Si. And this is why I went through this entire experiment before with the square root n partition matroid, right? Because the quadratic growth that we saw there turns out to be the exact same quadratic growth that we see here when we study the parts of the matroid through the lens of the circuit trigger parameter. Right, so in particular, if we revisit this algorithm from a couple slides ago, and you imagine that you've peeled off sets Si1, Si2, all the way up to Siq, and these are sets of similar sizes, this useful form of the growth rate lemma will tell you that the alpha value of the qth set you peeled off is growing as omega of q squared. Right, that there's a quadratic growth in these alpha values when you peel off sets of similar size. Yeah.
There's no probability in this statement?
There will be like a with high probability, yeah. I'm just kind of hiding that. And there will also be like conditions on like how close alpha is to magnitude S and so on, but yeah, exactly. Everything here is probabilistic, yeah. And now let's even actually take a look at why this is true. Right, let's imagine that we're running our algorithm, and then in some round you peeled off a set S, and then in a later round you peeled off a set S prime, which is of the same size as S. And now let's look back to the point in time when you peeled off the set S. And so S is what's just been peeled off. S prime is a later set that we're going to peel off. And now let's do the random permutation experiment. Right, let's sample a random permutation over all of these elements. Right, and the question is, when S collects its alpha of S element, how many elements have appeared in S prime by this point? Right, when you sample a random permutation, you're counting how many elements have appeared in S, how many elements so far have appeared in S prime. And the question is, once S gets alpha of S many elements, how many elements does S prime? And okay, I won't give you a formal proof, but morally, right, if you're trying to get alpha of S elements in S, what you're basically doing is you're doing like a random sample at rate alpha of S over magnitude S. Right, in order to collect alpha of S many elements in S, the permutation is basically a random sample of alpha of S over magnitude S many elements. And so when you ask, how many elements then have landed in S prime? Right, S prime is the same size as S. So certainly the expected number of elements is exactly the same as in S. Right, so the expected number of elements in S prime by this point is alpha of S. But importantly, as we saw before, there's also an inherent standard deviation here. Right, that there's a standard deviation of square root alpha of S many elements. And so what does this mean? An equivalent statement is that when you take your random permutation over these elements, there's an omega-1 probability that before S collects alpha of S many elements, that S prime collects alpha plus square root alpha of S many elements. And right, so if you assume for the sake of contradiction that alpha of S prime was smaller than this quantity, then when you ran this experiment, you would have actually recovered a circuit in S prime. Right, but this is a contradiction because the only circuits we recovered kind of defined the set S. Right? S is the set, like, defined to be the set of elements that were recovered in some circuit. So maybe to summarize this another time, for each random permutation, right, there's an omega-1 probability that S prime collects alpha plus square root alpha many elements before S collects alpha many elements. And so unless alpha is at least this big, alpha of S prime is at least this big, then almost certainly over your polynomial number of permutations, S prime will have also contributed some circuits in this round of the element. Everyone good with this?
So thinking about this as like budgets or something in different partitions, you're saying the fact that S prime was discovered later means that it has to have a much larger budget because otherwise you'd like pin it.
Exactly. Otherwise, you would have learned it at the same time. Yeah, exactly. That's the intuition to keep in mind. Perfect. Again, then as I promised you before, if you peel off sets of similar sizes, right, this is telling you that after n to the 1/3 rounds, the alpha value is growing quadratically, and so it would reach n to the 2/3. And so at this point, all the peeled sets have size at least n to the 2/3. So there's at most n to the 1/3 many rounds before you've recovered the entire matroid. And I should say that, okay, here I'm assuming the sets are similar sizes, but you can just do geometric grouping, and the argument still goes through. The growth rate lemma isn't that sensitive to like the ratio of sizes between sets. All right, so now with that established, hopefully we have some intuition for how things work in partition matroids. Now I'll just briefly describe how things work in the general matroid case. And as I mentioned before, I won't actually give you a complete proof of like the n to the 3/7, and I won't even actually give you a complete proof of the n to the 4/9 run algorithm, but I'll at least hopefully give you some intuition about how things work in this setting. And so as I mentioned before, the key insight is that we're really going to build off of what happened in the setting of partition matroids. But the key question is that now when you're talking about arbitrary matroids, right, things are not guaranteed to be as nicely structured. Right? There's not even necessarily an analog of what is a part in a general matroid. But let's think about what properties are actually very useful for us when we were talking about partition matroids. In particular, one thing that was very useful for us was that when we did this random permutation experiment, and we peeled off a set S, of all the parts that had contributed circuits, what we wanted was that the set S contains the first circuit C that appears in a random permutation with high probability. Right, and like when we talked about the partition matroid setting, this was essentially how we defined the set S, right? S was the set of all those circuits who did appear at some point. And so I call this the circuit containment probability, and this was key for us when we were trying to argue about this growth of the alpha values, right? That we get this quadratic growth in the alpha values between subsequent rounds. And it turns out that this same thing turns out to be key when we talk about arbitrary matroids. And so to make this a little bit more formal, again, we're trying to formalize this circuit containment property. And so we're going to try to define a part. And in order to do this, we define a new quantity. And so let's imagine that we have a matroid with ground set E and independent sets I. For a subset S of elements, we let Q sub M of S be the probability over a random permutation pi that the first dependence that appears under pi is contained in S. Right, so I call this the circuit containment probability. It's the probability that the first circuit is contained in S. And what we saw before is that we want this probability to be large. Right? In the previous algorithm we saw, we wanted this probability to be like 1 minus 1 over poly n. We're not going to ask for something quite as strong here. But in general, we say that a set of elements S is a part if this circuit containment probability is at least 1 minus the low of 1. And if we just had that condition, okay, it'd be pretty trivial to define a part, to find a part in the matroid. You could even just say that the entire matroid is the set S. So importantly, we also have this secondary non-triviality condition for the set S, which says that when you do your random circuit experiment, every element X in your part S has to appear with non-trivial probability in these circuits. Right, so it's not enough just to contain all the circuits with high probability, but it has to be a set for which these are the elements that are frequently appearing in those circuits C sub I. And so this is to ensure that the part you peel off is actually somehow you can imagine it's like a well-connected part where these elements do frequently appear in circuits. And I won't go into this, but it turns out that you can actually compute these parts of a matroid in just one round of polynomially many queries. Right? And I should mention that just taking one glance at this, it shouldn't even be clear that these kinds of parts exist in arbitrary matroids. But nevertheless, turns out with some careful implementation, you can even find such a part in just one round of a polynomial number of independence queries. But I will say it's like a large polynomial here, like n to the 10 or something.
But if you go back to the partition matrix, then this gives you the set, the union of all the smallest blocks.
Exactly. That's what it would be. It would just be the union of all those small sets that you saw at the beginning. Yeah. Perfect. And now the key point is that with this notion of a part in a general matroid, you actually can construct a matroid decomposition just like we saw for partition matroids. Right, so given a matroid M, you can decompose it into sets S1 through Sk, such that each set S sub I is a part. And I say with respect to E minus this union, all I mean is that E1 is a part of the matroid, but then once you peel off E1, S1 is a part with respect to E, and then S2 is a part with respect to E minus S1, exactly. Not only this, but again, we have the same kind of functional version of the growth rate lemma, which says that if the two sets are of similar sizes, then again, you get this quadratic growth in the alpha values. Not only this, but if you do this decomposition in K rounds, if you recover K sets in this decomposition, you can do this in just K rounds of a polynomial number of independence queries. And using the exact same logic as before, you can even show that the alpha growth rate ensures that this is always going to be bounded by just n to the 1/3 many rounds. And so this kind of is like a very functional decomposition, which decomposes the matroid into a bunch of well-behaved pieces. And so you might be wondering, okay, if you can do everything now in n to the 1/3 many rounds, why doesn't it just give you an n to the 1/3 round algorithm for finding a basis of a matroid? Right, it's a tempting question to ask. The reason why is that in arbitrary matroids, right, these parts don't have a super nice structure the same way that pieces of a partition matroid have a nice structure. Right? You can have a very non-uniform structure, even though you satisfy the circuit containment probability and the marginal probability conditions. And so what we do is we show that nevertheless, given your alpha value and your marginal probabilities and your circuit containment properties, there are still ways that you can process the matroid, these pieces of the matroid, to guarantee progress towards finding a matroid basis. And so in particular, you kind of condition on what the alpha values are. And if the alpha value is big, you'll make progress by finding a big independent set in the matroid. Maybe if the alpha value is small, you'll instead make progress by discarding many redundant. And so now you kind of do a case analysis based on these individual pieces that you recovered in the decomposition. And so I won't prove these claims for you. I'll just say these kind of subroutines for making progress towards finding a basis. And then I'll leave it at that. We'll kind of take it at face value that careful case analysis would indeed give you a better algorithm. And so the first claim is that whenever you recover a part S, you can find an independent set in the parent matroid of size alpha of S divided by magnitude S times N. And this is just using one round of a polynomial number of queries. And so again, I won't prove it to you, but maybe we'll go through an example about how exactly you can expect this thing to come about. So let's revisit the lower bound from KUW. Right, so this is the partition matroid. There's n to the 1/3 parts. Each is of size n to the 2/3. And the budgets have the staircase I times n to the 1/3. The first part, when you run this algorithm, would be P1. You've recovered only the first part. And so naturally then the alpha value, which is again the median location of the first circuit, would just be the budget plus 1. Right? So it would be n to the 1/3 plus 1. And so this claim is telling you that you can then find an independent set of size n to the 2/3 in this matroid. Right? If you plug in magnitude S, alpha, and n, it would give you n to the 2/3. And that's actually very easy to see, right? Because if you just sample every element in the matroid at rate just a little bit less than 1/n to the 1/3, then you would indeed expect to collect n to the 2/3 elements without any dependencies. Right, so that's like one functional way to think about this claim. The second claim is a little bit more intricate and is now talking about the other side of the coin. Right, you're given one of these parts of a matroid, but now the alpha value is small. And you're asking how well can you do when it comes to deleting elements? And so here we claim that given such a part S, you can always find these like redundant elements that you can delete while still preserving the existence of a basis. And the number of elements is basically just S squared over alpha of S squared. And so this is the key place where we have like a weakening compared to partition matroids. Right, so when you recover a piece of a partition matroid, you're basically guaranteed that you can delete magnitude S minus alpha of S many redundant elements. For us, even if alpha of S is like, say, S over 2, that doesn't give you anything meaningful here in terms of deletions. Right? I mean, okay, it still gives you something nice, right? Like if alpha is less than square root magnitude S, then it's telling you that you can delete omega tilde magnitude S many. Okay, but I know I'm coming up on time here, so this is basically the last slide. Once you're given these two claims and the growth rate lemma, you just carefully do your decomposition. You pay attention when you use claim 1 to find independent elements, or claim 2 to delete redundant elements. And then you just keep repeating this until you can find the basis of your matroid. And so that's the last slide. Yeah, thank you so much for having me. It was my pleasure to be here.
Any questions?
Yeah.
Do you have an example where you're in the deletion part of your subroutine, you know what you cannot do as good as in the partition matroid?
So there are places where you can't do as well as partition matroids, but in general, we do think that you can still do like much, much better. Like in particular, we think that using our decomposition, there are likely ways that you can basically just do it a constant number of times and find a basis of a matroid. It's just that there's some like technicalities and like matroid concentration that we're not able to prove. But so we think that you should be able to nearly match partition matroids, just that we're not exactly able to. Yeah, and then you had a question as well.
Yes, do you have intuition for what is a part in a graphical matroid?
That's a great question. So it will somehow be like the union of like the shortest length cycles, basically. But yeah, I don't know what that like operationally means in a graphic matroid. But yeah, somehow the union of the shortest length cycles. I think there you have some nice properties where like the sizes of the cycles satisfy like a smooth counting bound. And so when you do your random sampling experiment, with very high probability, you're only going to see circuits of this, like cycles of the smallest sizes. And so it should just be like a union of those smallest simple cycles. Yeah.
Is this like a Karger bound for counting Karps?
Yeah, so there is like a Karger bound for cycles and graphs. Yeah.
Okay.
And so that's when you do this experiment, you would only see those like small. Yeah, it's exactly analogous to Karger.
Okay, so the growth rate lemma I should think of as a general.
No. So in general, the growth rate lemma is not quite Karger, but in graphic matroids, the growth rate lemma is somehow, or like the random permutation experiment is like Karger. Yeah, I'll say that.
Okay.